So today I want to talk about the quest for physics beyond the standard model, which is one of the holy grails of particle physics, and I've subtitled it "Facts." So I'll tell you some actual facts about physics beyond the standard model. Fancies, meaning speculations or imaginings about what the underlying physics beyond the standard model is. And then I'm going to, at one point, express strong opinions about certain matters. This was intended to be slightly controversial. I've given this colloquium a few times, around the country and internationally, and I haven't irritated anyone yet, I think. So I'm a little bit disappointed, but maybe my luck will change today. But it's no longer work.
Okay, try now.
Okay, great. All right, so it's in three unequal parts. The first one is something I call the story that was to be, which will be most of the talk. And then developing plot lines. I'll have an account of current indications for physics beyond the standard model, but mainly about indications that we had until recently and are going away or have gone. So part of this will be a story of the high emotional ups and downs that we go through in this game, and then a very short and rather a speculative section about to be continued. Okay, so the story that was to be. So I've been in the game a long time, since the 1980s, and I just want to set the scene then where we were at. So these guys, Glashow, Salam, and Weinberg, had already won the Nobel Prize for the standard model, even though key features of it, the W and Z bosons, had yet to be discovered as real particles in colliders, although that did happen in the early 1980s, and it's my earliest memory of a big result in particle physics, and I remember how exciting that was, even though the W and Z particles were entirely expected. Still, it was very exciting that they were actually found. I had a colleague who was working on UA2, one of the experiments that did this, and he was jumping up and down. So at that point, with the Nobel Prize given to the theorists, and with the W and Z bosons now created as real particles, not just seeing their virtual effects, the standard model was pretty much established. Of course, not completely yet. The top quark, which is necessary for the structure of the standard model, have yet to be discovered. And the reason is its mass turns out it's very high, 170 GeV or so very high. It was eventually discovered in the 90s. The tau neutrino, which interacts in a very subtle way. And to this day, we've only seen a handful of tau neutrino events, but that has now been discovered. And of course, the Higgs boson, which dramatically was discovered in 2012, and I'll come back to that. But at this point, that had yet to be found, but it looked like the standard model was holding together. Another development that I remember when I was a student in the 80s was the rise of particle cosmology, especially with the success of Big Bang nuclear synthesis. It was, getting to the point where the hot Big Bang was really starting to outdo all of its rivals, and that nuclear and particle physics in the early universe was seen as very important and successful, especially through BBN. And it turns out that this is important in the story of BSM. Okay, so in the 80s, early 80s, what were the indications for physics beyond the standard model? And here I'm talking about empirical indications. We can also talk about theoretical problems, and I will, but let me start here with empirical problems, because if you see issues in experiments, you know that that's part of the real world if the experiments were done correctly. So there was the solar neutrino problem. So Davis and collaborators wanted to confirm that the sun was a thermonuclear reactor, and one way to do that was to detect neutrinos. Here you see his detector down this Homestake mine in South Dakota. I went down there some 10 years ago or so, and actually went into the cavern where this thing used to be. It was no longer there, of course, but it was nice to be down there. And of course, famously, what he saw was a flux that was a factor of 3 lower than the theoretical computation of what the solar neutrino flux should be. But this was controversial because there was no independent confirmation that all the details, intricate details of the mathematical modeling of the sun was actually correct. And also, if you have a look at the temperature dependence of the neutrinos that were actually being detected by this thing, which are called boron 8 neutrinos, the temperature dependence was t to the power of 20. Okay, so if you just got the temperature wrong a little bit, you changed the flux a lot. So maybe a factor of 3 was not a big deal, all right? So it was there, and people were talking about it, but it was controversial. It was not completely clear that this was an actual. It was a problem of some sort. It wasn't clear that it was an indication of new particle physics. There was the dark matter problem, which was starting to be talked about, and I didn't know what to make of this as a junior student. And I think in general, it was early days for particle physicists thinking about dark matter. For astrophysicists, I'm not sure. Probably they got serious about it a few years before. And there was the matter-antimatter asymmetry of the universe, which should arise through some general process called baryogenesis. So here, coming back to dark matter, we see one of the pieces of empirical evidence for dark matter, which are the flat rotation curves of spiral galaxies. I'm sure you've seen this many times. And here we have Andrei Sakharov with Comrade Gorbachev there in the background. And of course, Sakharov, scientifically, one of the things he's famous for is determining the general conditions under which a particle-antiparticle symmetric universe at the Big Bang turns into one where there's a bit more matter than antimatter. So he determined the general conditions under which a theory would produce this. This is called baryogenesis. But of course, he was bravely sort of very active in politics as well. And I really like this picture. Oh, I keep meaning to change the date. Let's imagine that's 2025. So what are the indications for your beyond standard model physics today? And the answer is the same as it was in the early 80s. As neutrino masses, which is neutrino oscillations, that's what explains the solar neutrino deficit. There's dark matter and there's baryogenesis. However, things have advanced, especially in the first two. So this heroic suite of experiments have now firmly established neutrino flavor oscillations. And not only that, they've established that mass mixing is the driver of these flavor oscillations. And here there's this famous slide from the Neutrino 1998 conference in Japan. I was actually there for this talk. I remember it vividly. In 1998, it was still overhead transparencies and writing on it. You didn't spend 3 days writing a talk with PowerPoint. It was much quicker. So a very famous slide, and 6.2 sigma evidence, not from solar neutrinos, but from atmospheric neutrinos. These are neutrinos produced when cosmic rays collide with particles in the atmosphere, and you get neutrinos. And you see here this deficit of neutrinos compared to the expectation without oscillations. And dark matter was also is now absolutely firmly established that there is something like dark matter that is needed both cosmologically and astrophysically. So it is very firm that all three of these things constitute incontrovertible evidence for the existence of physics beyond the standard model. So one of the take-home messages is that physics beyond the standard model exists. Okay, it does exist. We have the empirical proof for it. Okay, now with all three of those, it's not that we're clueless how neutrinos may get mass. It's not that we're clueless about what the dark matter could be or how baryogenesis could happen. Actually, the problem is kind of the opposite. We have many, many, many ideas about all three of these things, especially neutrino masses and dark matter. And here you see a famous plot by Tim Tate from Irvine of all the different dark matter candidates that have been explored in the literature. So not wanting you to take home anything about this apart from the fact that there's a lot of them, okay? And so we have many ideas, but we don't know which ones are correct because we need experimental guidance. And it turns out the experiments are difficult to do, or we haven't got lucky enough yet with an experiment to tell us, for example, what the dark matter is. Is it a WIMP? Is it an axion? Is it a primordial black hole? What is it? Okay, there are also theoretical motivations for beyond standard model physics, and I list some of them. So an issue that has dominated theoretical thinking in this area for a long, long time are hierarchy problems. So by this word, I mean ratios of mass scales or powers of mass scales that are either very small or very large, depending on how you write the ratios. Here I've written them as very small numbers. And so these are unexplained small numbers. So the electroweak scale, the fundamental scale of the standard model, is about 100 GeV. Fundamental scale of quantum gravity and Planck is a lot higher. So we have a hierarchy of 10 to the minus 17. This is a very famous one. This is the cosmological constant, dark energy, and compared to the Planck scale to the fourth, as particularly highlighted by Steven Weinberg, it's a very, very small number. And also just the fermions in the standard model. If you compare the neutrino mass scale or the upper bound on the neutrino mass scale, which is actually all we know at the moment, with the top quark mass, which is the heaviest particle we've ever discovered, even that is a rather small number, 10 to the minus 12. Part of that is also this concept of naturalness. So this is a more technical thing. So naturalness is when, for some reason, you need some conspiracy between parameters. It might, for example, be that a ratio of masses is very small, or it could be some relationship between dimensionless parameters, and you need that for some reason. And you arrange for it, so you make that relation true in the Lagrangian that you're using specifically. But then there are always quantum corrections, there are loop corrections and so on, and the question is, are those relations preserved? And in some cases, they're not preserved by quantum corrections, and therefore, there might be a hierarchy or a special relationship that you need for some good reason, but theoretically it's unstable, right, when you compute to higher orders. There are fine-tuning puzzles. So there's a parameter in QCD called theta, which I won't explain, that needs to be rather small, less than 10 to the minus 10. This is called the strong CP problem. In cosmology, there's a spatial flatness and homogeneity of the universe. If we just have standard radiation-dominated hot Big Bang, then there are fine-tuning problems. The initial condition at the Big Bang has to be very close, very special in order to reproduce the large, homogeneous, spatially flat universe we see today. Another one is lack of unification, which people have worried a lot about over the decades. So we have the strong and electroweak forces and then gravity, and they're all separate forces with separate strengths. And there are a bunch of others. We have 3 families of quarks and leptons. Why? We still don't know why muons exist, for example. We have all sorts of masses and mixing angles for the fermions. Where do they all come from? We can worry about the origin of various things like parity violation, charge quantization, the origin of large-scale structure of the universe. Actually, I feel I should make that one more prominent. Anyway, all sorts of theoretical problems to worry about and have been worried about by many people. Okay, so now I want to come to the story that was supposed to happen, according to many people. All right? So I have 3 columns. The beyond standard model physics that people were thinking about and enthusiastic about, the purported benefit of that BSM physics, and then the prediction, if there was one, how to actually get evidence for this experimentally. So the first one is unification. And setting gravity to one side, one can think about unifying the strong and electroweak forces, and indeed, we've known mathematically how to do that for 50 years. We call these theories grand unified theories. They exclude gravity, but they're still rather grand. And the kind of benefits and basically what you do is you take the gauge group of the standard model, SU3 cross SU2 cross U1, and you embed that in a bigger group as a subgroup, like SU5, SO10, and so on. All right, so the benefits of grand unification are, it explains a certain parameter in the standard model that has to do with electroweak interactions, the sine squared of the weak angle. some versions of the theory had a good explanation for the bottom to tau mass ratio. You could explain the quantization of electric charge, and going back to near the genesis of grand unified theories, which necessarily have baryon number violation in them, and baryon number violation is one of the Sakharov conditions for baryogenesis. Well, it looked like gut theories gave you baryogenesis as well. And it had a dramatic prediction, which I was reading about as a high school student in the 1970s, which was proton decay. And I remember reading very enthusiastic articles where people were expecting proton decay to be observed, kind of just around the corner. Then there's electroweak scale supersymmetry, or SUSY. So this kind of developed in concert, a little bit later, but in concert with grand unified theories for a certain reason. One thing was that in grand unified theories, without supersymmetry, you have the electroweak scale and the grand unification scale, which are about 14 orders of magnitude apart. And this is where there's a radiative stability issue. And if you consider loop effects and you don't do any fine tuning, then what you'll find is that the electroweak scale gets pushed up to the gut scale, and that's bad. But with supersymmetry, you could remove that deleterious feature, and so the electroweak scale was stabilized. And this was really the driver of thinking about supersymmetry. Certain versions of it, you got WIMP dark matter, weakly interacting massive particle dark matter. And also, if you looked at the details of the unification of the strong and electroweak forces, it turns out that the particles in the standard model don't quite do it for you. You'll almost get there, but not quite. Whereas if you adopt supersymmetry, which has superpartners for everything, then you have good unification. And indeed, the prediction was we turn on the LHC and we find superpartners. Okay, partners of the electron, partners of the gauge bosons, etc., squarks, gluinos, all these sort of things. Then, more grandiosely, we could look at full unification. So not just the non-gravitational forces, but also gravity. And this can be done via superstring theory, which operates at the Planck scale. So the benefit here is it's a theory of everything, at least at the microscopic level. In the 80s, when string theory really hit in a big way, and this was when I was a student, so 1984 was the first string revolution, it looked like string theory could predict an almost unique universe, okay? And of course, you get quantum gravity out of it. On the experimental side, because the new physics is a 10 to the 19 GeV, well, there's a lot of new physics there, but it's not easy to access experimentally. But at least it was consistent with the concept of supersymmetry at the electroweak scale, because these are superstrings that have supersymmetry in them. And you need supersymmetry to get good string theories. So at least it was consistent with this picture. But then on the neutrino side, this is kind of less sexy, less dramatic. But the feeling was that neutrino masses probably should be non-zero. In the minimal standard model, they're exactly zero. But probably there's no deep theoretical reason for the neutrinos to be exactly massless. So maybe there's an extension of the standard model and neutrinos are not massless. This was consistent with views about grand unification, especially SO10. The prediction, apart from the existence of neutrino oscillations themselves, was that the oscillations should have small mixing angles. So in the quark sector, there are these things called mixing angles, all right, which tell you in weak decays how much of the time you get a down quark and how much of the time you get a strange quark or a bottom quark. That's what mixing angles do. And in the standard, and there's a 3x3 matrix called the Kobayashi-Maskawa matrix, which describes that. And it's observed to be almost the identity matrix. Not quite, but almost the identity matrix. So that's called small mixing. And the idea was that since we believe in grand unification, and in grand unification, leptons and quarks are related to each other by transformations, and since quarks have small mixing angles, so should leptons. And that means neutrino oscillations should proceed with small mixing angles, okay? And this was really important for the solar neutrino problem, because remember I said that was a factor of 3 deficit. But with small angles, you wouldn't expect a factor of 3. You'd expect, a percent of something. However, there was this beautiful thing called the MSW effect, which was a resonance effect, which occurred when neutrino oscillations happened in matter, which would amplify mixing angles from small to large. So it was thought, because of things like the MSW effect, that you could have small mixing angles for neutrinos, that they're partnered with quarks in grand unification. Everything is very nice, and you can still explain the solid neutrino problem through this resonant amplification. Okay, so that's what was supposed to have happened. So now I want to get to the scorecard of this. So we're still waiting for proton decay. Hyperchemiocandide is being built, the gigantic water detector, water Cherenkov detector. One of their physics goals, apart from oscillation searches or oscillation measurements, is to discover, to continue searching for proton decay. All right, so we're still waiting. No one's saying protons are absolutely stable, but 50 years after I was a high school student, we're still waiting for that to happen. Superpartners. When we switched on the LHC, they didn't leak out of the detectors, okay, or into the detectors. We have yet to see any indication for any superpartners. Not to say they're not there, but we're still waiting for them. Here's a success. Indeed, neutrino masses are non-zero. So that hunch was correct. So that's worth a few exclamation marks. And this was just plain wrong. Just plain wrong. So neutrino mixing angles are actually large. And I'll come back to what lessons one might draw from that in a moment. Okay, now I want to make some comments about especially the middle column, because I grew up, when I was a student, I grew up in the era when guts were becoming well developed and supersymmetry was coming along. And you would hear talk after talk after talk about how it's almost inevitable that beyond standard model physics is a supersymmetric ground unified theory. So I want to talk about the things that were being said and comment on them. So let's first talk about the m beta m tau mass relation, which was argued to be a great success. Well, they're not the only particle masses we have. We have all the other fermions, and it is not possible. It has proven to be impossible to get predictive relations that are also correct. It's very easy to get predictive relations, but when you do, they're inevitably incorrect. All right. So to get a grand unified theory to actually fit all the fermion masses, well, you have to complicate the theory. And when you complicate the theory, you remove a lot of the benefits that you wanted to get from introducing a higher symmetry. Well, there's other ways to understand charge quantization. I won't go into that. Gut baryogenesis was a great idea that developed in the Soviet Union in the 1970s. But then when inflationary cosmology was seen as necessary to solve problems in cosmology, that ruled out gut baryogenesis. So it got morphed into something else, leptogenesis, which is very useful. But gut baryogenesis turned out to be a furphy. Is the electroweak scale indeed destabilized? This requires a very subtle discussion, which we do not have time for. There's no evidence in favor of WIMP dark matter as of today. A lot of experiments have been done looking for it. It could still be WIMPs, but at the moment, despite many years of decades of experimentation, there's no evidence that it's a WIMP. Okay, the almost unique universe from superstring theory. In the late 1980s, I spent a lot of time, a couple of years, working on things called superstring-inspired E6 grand unified theories, because it was argued that was going to be inevitably the low energy limit of superstring theory, which would explain everything. It came from heterotic E8 cross E8 string theory, if you know what that is. So I thought, well, if that's the case, we better learn about this and put a lot of effort into it. And then when the string theorists, of which I am not one, learned more about string theory, especially with the advent of these things called D-branes, all hell broke loose. And now there are something like 10 to the 500, essentially different kinds of string theories. Technically, these are different vacuum states of probably some unified underlying theory. but still 10 to the 500 or so different choices for what the universe could be like if string theory is correct. So not even close to a unique universe, all right? Still have quantum gravity though. And with it, if you put the string landscape together with eternal inflation, that's where you get this notorious thing called the string multiverse, which I'm sure you've heard of. Now, as I already said, this was just plain wrong. There are actually two large angles. There are three Euler angles. Two of them are definitely large, and one is not too small, theta 1,3. And this led to a lot of revisionism. And this is a thing I really don't like. So, but before this became clear, so first of all, the solar neutrino problem, this factor of 3 deficit, it was supposed to be in vacuum, the responsible mixing angle is small, and then it gets amplified by this subtle resonance effect, very beautiful. That's wrong. It turned out that the solar mixing angle is large. And in fact, it's the S in MSW, Alexei Smirnov, who's a good guy. I remember he wrote a paper saying probably it's actually not the small angle solution, but it's this thing called the large angle solution. And the other large angle comes from the atmospheric neutrino anomaly. I showed you the slide before from 1998. And what happens psychologically for theorists working on neutrino mixing is that before this became established, both those things, you knew that neutrino mixing angles were small because quark mixing angles were small, and you believed in unification. This is what you believed. If you believed anything other than that, you were considered eccentric. Okay. As soon as it became clear that at least two of the three mixing angles are very large, almost overnight, theorists said, we never really thought that neutrino mixing angles would be small because after all, neutrinos are different particles. They can be their own antiparticles, so-called Majorana fermions. They're probably Majorana because they can be. And then therefore they're a completely different kind of fermion to the other quarks and leptons. So of course we don't expect the mixing angle patterns to be similar. And it continues like this to this day. So there's sort of this step function in the rhetoric, right? And I don't know, I find that irritating. All right, now let's turn to the New York Times. So this is an article from 2017. It's a bit old, but it's still relevant. So physicists monitoring the LHC, seeking clues to a deeper theory, but the silence from the frontier has been ominous. So the LHC switched on, we discovered the Higgs boson, but we did not discover any beyond standard model particles in 2017. It remains true today, and in particular, we didn't discover supersymmetry. So what did they say? So Adam in Paris says the feeling in the field is at best one of confusion and at worst depression. Gian Giudice, still the head of theory at CERN, these are difficult times for the theorists. Our hopes seem to have been shattered. We have not found what we wanted. And okay, so there's a connection here with Denmark, my Danish colleagues. So apparently there was a meeting in Copenhagen where a typical sort of physicist bets were made, which didn't involve your house, but did involve bottles of expensive cognac. And so Herman Nicolai says, many of my colleagues are desperate. They've invested their careers in this. And what they have invested their careers in was supersymmetry, which was supposed to be found when the LHC switched on. As I say, it still might be there, but sort of hiding from us in some way. But anyway, a lot of people were surprised that it didn't immediately manifest itself. So this supersymmetry was a hidden mathematical beauty, like a golden apple, you know, at the core of reality. I would just like to make some emendations of this. So this reads like there was complete unanimity that this was what we expected. And, you know, I would say this was certainly the majority view, but it was not unanimous, all right? So it's not like it was inevitable that supersymmetry would exist. Okay, a few other comments. There's the cosmological constant. So this has been a persistent issue in physics beyond the standard model, especially in cosmology. So this was supposed to be zero until the discovery of dark energy. The theoretical prejudice was that the cosmological constant, we knew it was small. And so once you know something is small, then you say, well, naturally, we would expect it to be exactly zero. The problem was no one has been able to think of a reason for why it should be exactly zero. But the hope was that we're just not smart enough, and eventually someone will come along and find a reason for that. So the idea was that cosmological constant was just meant to be zero. We don't know the reason, but one day somebody super smart will discover the reason, right? Well, and then dark energy was discovered. So certainly the situation is complicated. It's maybe even more complicated than had been thought to be the case until a few months ago. So I'll come to that because it may not even be a constant. We still have no clue about why we have three families of quarks and leptons. So I've mentioned it, but I haven't explained it. It's like we have an electron and then two heavier copies, the mu and the tau. And the same for quarks and neutrinos. So we still don't know why muons exist. And we still do not know what is the origin of all the masses and mixing angles. The standard model just says, these are three parameters. And so, yes, in some sense, that's an answer. But in terms of what we might hope might be a deeper answer, which told us something about why we have three families and why the masses are hierarchical and so on, we still don't know, but it's a big topic, especially in the neutrino community. We have inflationary cosmology, so I haven't focused on this, but it is a very interesting and compelling paradigm, very well motivated in order to explain the homogeneity problem, the isotropy problem, the fact that the universe is very large, even the seeds for large-scale structure formation for galaxies and so on. It can all come from inflation. So a lot of compelling circumstantial evidence for something like inflation. But then you can ask, is there a deep specific model for it? And I haven't worked on inflation until pretty recently, and I'm not an expert on it by any means. But I've been hearing talks about inflation for decades. And what struck me was that it's an idea, it's a paradigm. But if you ask, is there one model that is considered to be the favored model? There wasn't such a thing. They all had their drawbacks. But in recent years, there's two things. There's something called Starobinsky inflation, something called Higgs inflation, which I think are the best we've done so far about maybe establishing an underlying rationale for why inflation happened. Then there's the strong CP problem and axions, which are a byproduct of solving the strong CP problem. And axions can be dark matter. So, I think axions are very well motivated, and a lot of experiments searching for axions. But it could be that axion dark matter is there, but it's subdominant. That will make it harder to find. And there are various other issues. Okay, so now I come to the opinions part. All right, so this is the big opinion slide. So I want to learn some lessons from this history of the discovery of physics beyond the standard model, the search for physics beyond the standard model, which we didn't find, and what was happening in the theory community as all of this was happening. So lesson number one, according to me, is don't push partial successes as big successes. So yeah, this ratio came out right, but you have to do a lot more work to get the other ratios correct. And no one has been able to do that in a predictive way, in what I would really call a predictive way. You can get it phenomenologically fine, but then you lose all the predictivity of your theory. In my opinion, a paradigm is not fully believable until you have a specific, realistic, complete theory. So let me come back to inflation. It always seemed like a good idea, but I personally can't really believe it. Okay, if you could find smoking gun empirical evidence for it, fine. But absent that, if you can't even write down a good underlying theory for it, no matter how good your ideas seem, sort of in the big picture, unless you have a specific theory that really where everything works, I still have doubts about it. And the same is true for Suzy Gutz, actually. There are certain defects in these theories that we should be honest about, and people kind of were, but a lot of this was treated in a funny way. There's something called the doublet-triplet splitting problem in grand unified theories, something called the mu problem in supersymmetry, the quark-lepton mass relations I've mentioned, and actually in supersymmetry, there's the question of how you spontaneously break supersymmetry, because if supersymmetry were an exact symmetry, then the superpartners have exactly the same masses as electrons and so on. And that's not true. And there's still big issues with how supersymmetry breaking should happen. So I think it is important to acknowledge that even a beautiful idea, when you try to implement it in a physics theory, well, the idea might be beautiful, it might be mathematically beautiful like supersymmetry, but then when you implement it in a physics theory and you need to explain the real world, if you run into problems, you need to take those problems seriously. Okay, and maybe it should lead you to think more broadly about what might be the solutions. Okay, be humble and don't ignore sensible alternatives. What tended to happen is that speculative ideas, including grand unification, supersymmetry, small mixing angles for neutrinos, these became sort of or WIMP dark matter. These became enshrined as things that all right-thinking people believed. Okay, and I think that we should have firm orthodoxy for well-established physics. So the standard model of particle physics is well established. The existence of dark matter is well established. But even things like superstring theory are not well established. Okay, empirically, they're just not well established. And so all those things have to be considered to be speculative. After all, in the end, we're an experimental science. So it's not just about the beauty of ideas or the theoretical structures. It's about whether they actually are there in nature. Don't jump the gun. So there's a tendency in the theory community, particle theory community, to believe results without them having an actual firm foundation and proof. So in particular, in the 80s, in the 80s and into the early 90s, this disappointed me that the string theory business of probably there's an almost unique universe that we can explain is a mirage, and that's because we didn't understand enough about string theories. And when we did, string theory, the history of string theory, I'm not a string theorist, in the 1970s, only very few people worked on it because most people thought that it's so difficult to write down a consistent string theory that probably it's impossible. And then what happened in 1984 is that Green and Schwartz proved that it in fact is not impossible and presented some examples of theoretically consistent superstring theories. But it was still very hard to do, and you had to have very special conditions like E8 cross E8 SO32 symmetry groups, right? Still some very special conditions. So it still seemed like string theory was so hard that it was almost unique. But then all hell broke loose with the discovery of D-branes and blah, blah, blah. And suddenly now we have this string multiverse of 10 to the 500 possible universes. So, there was a lot of jumping the gun. Just because in the 70s, it seemed to you it was very, very difficult to even write down one consistent string theory. Well, the reality was there were 10 to the 500 of them, okay? So you shouldn't have made that conclusion because it was not a mathematically rigorous conclusion. It was just on the basis of lack of imagination, lack of progress, didn't know what to do about it. But in fact, these theories were there all along. And don't be a revisionist. If you held the view that experiment disproved, like small mixing angles for neutrinos, just acknowledge it. This is what I thought. I had my reasons for thinking neutrino mixing angles were small. Turns out they're not. Fine. That's life. That's what we do. But that's not what every theorist does. All right. So the previous orthodoxy, the story that was to be, is not quite dead. But there are some worrying symptoms in the sense that if it is there, then it's all these things are hidden from us in some way. Proton lifetime is longer than initially expected. Superpartners are hidden from us in some way, and so on. So they're the worrying symptoms. Now, all of this is based on the desire to explain more using larger symmetries, okay, granulified symmetries, and so on and so forth. And I like that too. I've spent most of my career thinking about higher symmetries, and this is a big frustration that there are very obvious things mathematically. The way SU3 cross SU2 cross U1 fits inside SU5, which is the first granulified theory published, it's obvious. It's mathematically obvious. It's mathematically elegant, okay? So surely it's true. Well, we don't know yet that it's true. And this is a big frustration, right? Because if you're on the track of something that's right, it should just work, And if something hasn't worked after 50 years, you have to sort of wonder about it. So it is frustrating. So let me talk about parameters, because this is one of the things that higher symmetries are meant to do for us. It is to shed some light on this plethora of parameters. So I just wanted to write them down for the standard model, including Dirac neutrinos. So Dirac neutrinos are those that are different from their antiparticles. If we have Majorana neutrinos, the number of parameters is even more. So we have the various masses. These are the masses of the neutrinos, charged leptons, quarks. Here are the mixing angles. There are 2 CP violating phases. We have the strengths of the electroweak force here. We have the fundamental parameter of QCD, which is the confinement scale. We have this theta QCD I mentioned briefly. We have the Higgs mass and the Higgs self-coupling. So if you count them, that's 26 parameters in the standard model Lagrangian augmented with massive Dirac neutrinos. And this is the problem. That's the Lagrangian we would write down. If you wrote it out with all the indices there and so on, it's kind of this big, with many arbitrary parameters. So what we want is a better theory, a more predictive theory that sheds some light on these parameters. Could it really be that the fundamental theory of the universe has 26 parameters in it, and that's it, and we have to live with that? The suspicion is, and it's kind of a human thing, that there surely is a better theory with far fewer parameters in there. So can we find it? Well, that's what symmetries do for you. They certainly they certainly have the power to increase the predictive power of the theory by decreasing the number of independent parameters. However, you also need to ensure that the predictions you get for how parameters are related are experimentally justified, that they agree with experiment, and that everything is fine in your theory. And when you make that demand, unfortunately, usually the exact opposite happens. You wind up with a theory with even more parameters than the 26 in this standard model extension. And this is deeply frustrating. It's frustrating to me. So what goes haywire is of course, these higher symmetries, they're very nice, but we don't see them manifestly. We don't see that the strong and electroweak interactions have the same strength, right? So we have to break the symmetry, and the way to break it is spontaneously. And this is what happens. This is where it goes wrong. You have to spontaneously break these symmetries in order to agree with experimental results. But then the way you do that theoretically introduces more parameters than the ones you started with. So for example, in minimal SO10 gut, the prediction for, let's just imagine we had one family of quarks and leptons. They're all degenerate in mass, okay? And that's very strong prediction, very clear prediction of minimal SO10, and completely wrong, okay? So right from the start, you have to go non-minimal, all right? So realistic breaking, I won't explain how all of this is done, implies many new parameters. It often nullifies the predictions you're trying to make with the enlarged symmetry in order to get your theory to even agree with experiment. And it's frustrating. So I had hoped that we were doing spontaneous symmetry breaking incorrectly. I wrote many papers where elementary scalar particles like the Higgs, I thought of conceptually as just placeholders, that it would be replaced by something that would have fewer theoretical issues, composite Higgs particles or something else. Unfortunately, well, it's a great triumph, and this was a very, very exciting thing in 2012. And so this was us in Melbourne in 2012 at the convention center, where we kind of coupled in with the Higgs announcements that were happening for political reasons on CERN soil. And we're very, very exciting evening. So very exciting. However, from a theoretical point of view, this does complete the standard model, but it gives us no clue whatsoever up until this point that we were doing anything wrong in terms of our thinking. As far as we know, elementary spin zero particles, scalar fields are the way to go. And then it's fine for the standard model. When you try to use it in any BSM theory, that's when things go a little bit nuts. So we don't know what is the path forward. I think this is the issue: spontaneous breakdown of bigger symmetries. I wish I knew a really good way to do that. That is different from the standard mechanism and can be done in such a way where you have your enlarged symmetry and you get the benefits of it, that you don't try to hide its predictive power in order to agree with experiment, that you actually get something that works. I have no idea how to do that, and I don't think anyone else does. And this is all very puzzling. It's puzzling because, as I said, something like SU5 mathematically just hits you in the face. It's like, oh, so obvious. It just hits you in the face. How could it be wrong? And yet we still don't know if it's correct, you know? So, yeah, bad situation. All right, end of part one. So developing plot lines. So this is an emotional journey of the ups and downs of searching for physics beyond the standard model. I mean, I know we have neutrino map. Well, anyway, let me come to that. So back to New York Times. So Lisa Randall had written a book, Knocking on Heaven's Door. It was recent in 2017. And you know, knocking on heaven's door means the LHC, right? It will discover lots of things. But what if nobody answers when we knock on heaven's door? What if there is nothing new to discover? That prospect is now hanging like a cloud over the physics community. However, we still have non-zero neutrino masses, we still have dark matter, and we still have baryogenesis. These things need to be explained, and they can't be explained in the standard model of particle physics. So there's definitely physics beyond the standard model. We just haven't, through these things, and maybe other things like the strong CP problem, fine-tuning, density perturbations, etc., inflationary cosmology, all these things. What the problem is that the experiments and the observations we've done to this day don't do anything other than constrain possibilities. We don't have any positive indications about how any of this actually happens in real life, right? And that's what we need. But it's not because new physics doesn't exist. It does exist. We just haven't done the right experiments to find it yet, all right? Or maybe the experiments we need to do and the observations we need to make are beyond our technical capabilities and economic capabilities. That's certainly possible. I hope not. That would be extremely depressing, okay? Okay, another thing that can happen is that independent of these things, manna could fall from heaven, you know, something unexpected could fall in our laps. So for example, the muon, when that was discovered in the mid-1940s, it was not expected. They were expecting the pion. But before they found the pion, they found the muon, and that was not expected. Okay, so maybe manna from heaven will come down to us. And we thought we had some. All right. So I now want to talk about the anomalous magnetic moment of the muon. So the muon is a little bar magnet. So is the electron. And this guy Schwinger famously computed with great laboriousness this one loop correction in QED. To G-2 of the muon, the anomalous magnetic moment, and got this famous alpha over 2 pi, which I believe it's etched on his gravestone. All right, and it was a correct answer. And then heroically, Kinoshita-san has spent a career calculating G-2 of the muon in the standard model to ever higher precision. And in QED, it's up to 5 loops. So, you know, order alpha to the 5, where alpha is the fine structure constant. Really heroic calculations, which I couldn't imagine, doing myself. That's something I would do. Here's a bit of a glimpse into what these people have been doing. So we have almost 13,000 diagrams. These are these are five loop graphs. So these are 5 loop QED corrections to G-2 of the muon. And believe it or not, they've all been computed. Weak interactions also contribute to the G-2 of the muon. Hasn't been calculated up to 5 loops, but still up to 2 loops or something. And then also strong interactions affect the magnetic properties of the muon at higher order. And this is where the excitement recently was. So here we have a muon interacting with a photon, but in addition, a photon is exchanged between the two muon lines. And part of the time, the photon disintegrates into a group of strongly interacting stuff. This is called hadronic vacuum polarization. There's a similar thing here, which is called hadronic light by light scattering, but quantitatively, this is the more important effect. Now, the issue is that the experimental measure, so two things. The theoretical prediction, as I've explained, for G-2 of the muon and the electron is known to many, many significant figures, 10, something like that. The experiments now are also very precise. And they agree, except possibly in the last few significant figures, okay? So it was very, very important to compute very subtle things, like this is a very small contribution to G-2 of the muon, but we need to know what it is because its magnitude, theoretically, plays into the comparison between theory and experiment. So there have been two methods used to do this prediction. One is data-driven. So you look at E plus E minus to hadrons, the scattering cross-section, and there's a way using theory to relate that to this hadronic vacuum polarization. This is called the data-driven method or the R-ratio method. The other way is to just brute force compute it using numerical techniques in QCD. This is called lattice gauge theory. All right, in mid-2021, now this was getting very exciting because an old Brookhaven measurement of G-2 was confirmed by a new Fermilab measurement of G-2, completely consistent. And this was the consensus for the standard model prediction. And the deviation was more than 4 sigma. So it looked really, really exciting. No sooner had this happened than these guys, Budapest, Marseille, Wuppertal, lattice gauge theory collaboration, they came out with a new lattice calculation. And that, if you use their result, you got a value for G-2 that was not very, very different from the measured value. Now, before that happened, have a look at these red dots. So this was what you got from the R-ratio method. 3 independent groups, very, very consistent, right? So provided the experimental data they were using is correct, it looked like, you got quite a discrepancy from where the measurement was. These were the earlier lattice results, and they were there, but they had very large error bars, so they didn't really tell us anything. So the excitement was about this. And that's where this 4 sigma discrepancy came along. And then, as I said, no sooner had that been, had this new result been published, then BMW came out and got this new result with dramatically smaller error bars from the lattice. And so, two things. It seemed to be making the anomaly go away because this looked like an indication for new physics, some exotic particles in loops in the muon photon coupling. But if you believe this, much less compelling that there's any new physics. You can worry then about why the lattice result disagrees with these data-driven methods, and I'll comment on that in a moment. Okay. Recently, Fermilab updated, well, a couple of years ago, updated their measurement. And if you took the old standard model prediction, it got up to 5 sigma. And 5 sigma is the magic number, right, in particle physics. However, BMW actually continued computing things. And actually, I don't show it here, but their results got even closer to the experimental measurement. But another thing happened. This experiment in Russia remeasured the E plus E minus, the hadron's cross-section. And when you use their new value, rather than the old ones, those red dots I showed you before, again, you got something much closer to the experimental value. So it could be that the red dots were wrong because the experimental data was wrong in some subtle way. So this has set the cat amongst the pigeons. And just today, just before coming here, I looked on the archive and there's a paper, it's a white paper by the G-2 theory community, lattice gauge people, data-driven people, and so on. So we've been waiting for this paper for a couple of years because we wanted to know, should we believe BMW? I've only read the abstract, literally just before coming here. But it looks like they certainly believe BMW. And so their conclusion is that this anomaly has gone away, right? So this is the emotional roller coaster, right? This really should have been taken seriously, and I did, and many people did 2 or 3 years ago. Chava did as well, and this has gone away, right? And that's very unfortunate. Okay, I won't go through that. Let me talk about anomalies in B meson decay. So these are B mesons are those containing a bottom quark. So we have capital B mesons containing a bottom quark. Sorry, mesons are particle-antiparticle bound states. B mesons are those that contain a bottom quark. D mesons contain a charm. K mesons, kaons contain a strange. So here is another anomaly that disappeared, RK star. So LHCb had these measurements, and this was the standard model prediction for this ratio. So we have bottom quarks going to kaons and either muons or electrons. This was a test of E mu universality, which is one of the features of the standard model. And it looked like E mu interactions were not universal as the standard model predicted. All right, and this was really exciting. I was excited about this. However, then LHCb found a mistake in their analysis, and a couple of years ago, it became clear that, in fact, their measurements, their data are consistent with the standard model. So that one went away, and that was psychologically very, very disappointing. I'm almost over it. There is a remaining, though, discrepancy in the meson sector, and we can hope. This involves bottom quark to charm quark transitions, so B to D meson transitions. And here, the universality test is between taus and electrons or muons. And short story, this is the standard model prediction, and the average of all the experimental results is this red ellipse here. So there's quite a discrepancy. You see the individual experimental results are all the same, all over the place, but they're all pushing in the one direction, right? They're all clustering around this area. So even though there's a lot of scatter, it could be that there is something real here. So we can hope for that. So this remains. It's called RD star. That's the name of the anomaly. Coming back, so here's a nice plot by experimentalist called Patrick Koppenberg about a lot of these flavor observables. And these dots here are the experimental results. And if they were bang on with the standard model prediction, all the blue dots would be along here. So this tells you the so-called pull in number of standard deviations, how much the experiment is from the standard model prediction. So here we have two processes that went into the RK star ratios, RK ratio, these two here. Now, you see what's happened is that the ratio is now consistent with the standard model, right? It's consistent with 1. But the numerator and the denominator individually are not consistent with somebody's standard model prediction. However, as Peter and Ulrich will tell you, these individual decay rates include some standard model QCD corrections that are not, as far as I know, well understood. So it could well be that these discrepancies, which look impressive here, are actually not an indication of BSM, but rather of QCD effects. Let me know if I've said anything wrong. Here is G minus 2 of the muon. Okay, here is G minus 2 of the muon, and this is with BMW incorporated, and it's even closer now. All right, so what could all this mean? I have to finish up very quickly. So we have these 3 empirical things. We had these. Maybe we still have some B meson decay. Well, we still do have some B meson decay anomalies, and maybe they're real. And we have a bunch of theoretical problems. What are we to make of all of this? Are these independent issues? Might some of them be connected? Might they all be connected? And the answer is there are many ways to connect individual things. Let me just highlight one of them since I'm running out of time, axions. So it solves a theoretical problem, the strong CP problem. Also, there's a way to connect axions with baryogenesis. Let me not explain that. This is work I'm involved with. Axions famously are a dark matter candidate. The symmetry breaking scale that gives rise to axions is actually a very good scale for generating neutrino masses. So I'm working on a theory that explains all 4 of these things using axion physics. So this is just an example of how indications, both theoretical and empirical, the physics beyond the standard model, might be connected. This is a very famous one. So neutrino mass generation and baryogenesis can be connected through something called leptogenesis in a model of neutrino masses called the type 1 seesaw, which is probably the favored model. And actually, that's what I use in this axion theory in order to make all of these connections. So it could be that there is a really deep and intricate story happening here. It'll just take quite a long time to unravel all of this. So what would get me excited was if axions were discovered, if there was an indication that they were the dark matter, right? Other things as well, but I don't have time to talk about them. Okay, coming back to the cosmological constant, as I said I would. This is the equation of state parameter. If dark energy is a cosmological constant, that's equal to -1. Here are some recent results from the DAISY collaboration. D stands for dark energy. And there's an indication that maybe the equation of state varies with redshift. And therefore, we don't have a cosmological constant, but rather it's a time-dependent or redshift-dependent thing. And so we have dynamical dark energy. This, of course, is very, very dramatic. This is like life-changing stuff. Now, this all needs to be confirmed, okay? But let's say this is something to watch. All right, and to be continued. I just want to end with a radical thought. One of the things I teach is quantum mechanics, and I've done a little bit of thinking about the fundamentals of quantum mechanics, and it worries me a little that we blithely use quantum mechanics like it is exactly true for the whole universe, right? We use it in inflationary cosmology. We use it to get the swing multiverse. But we haven't tested quantum mechanics on cosmological scales. So maybe an issue with what's going on is that quantum mechanics is not an exact theory, just like other things are proven not to be an exact theory, like Newtonian mechanics or Newtonian gravity. This is an extreme speculation, but I think is very, very important. It's nothing to do with particle physics directly, to test things like quantum mechanics and, for that matter, special relativity, and try to find if there are deviations, because then that would change everything. That would really change everything. Think about quantum gravity, right? So if quantum mechanics is not exact, then the whole quantum gravity story changes, right? Or if special relativity is not exact, that changes gravity. So all these things are very, very important. Okay, so let me leave it there. Thank you.
Thanks a lot, Roy, for this very nice and clear talk. Are there any questions?
Thank you. Very nice talk. So to cheer us all up a bit, experimentally, what should we go ahead and measure? Do you expect anything to change in the next 10 years? Are there any experiments that are coming online that you're really excited about? Do you think FCC or CPC or whichever one will resolve any of this? Or are we just doing more of the same?
Very good. So I've been accused of being too pessimistic in the last part of these slides. So I should change them because I don't mean to be. So firstly, the search for what the dark matter is very, very important and could provide a breakthrough at any moment, okay? So the thing there is, because we don't know what the dark matter is, we should be doing a range of different experiments looking for different kinds of dark matter, and they won't all find something, of course. Only one of them, one kind of experiment will find something probably, unless dark matter for some weird reason is a 50-50 mixture of axions and WIMPs or something like that. But that would be fine tuning. I don't really believe that. So that's very important. So axions could be discovered more or less at any moment, okay, for example. So I think the search for dark matter is very important. Primordial black holes have made a comeback. It was thought they were ruled out as 100% of the dark matter. It turns out this isn't true. And asteroid mass scale primordial black holes are a viable dark matter candidate. And these can be searched for astrophysically through microlensing and so on. So, axions, WIMPs, primordial black holes, all very, very active avenues for research. There could be a breakthrough in any of those. Flavor physics, LHCb, which Ulrich is on, and others are on, Tom is on. Flavor Bell 2, which our people are on. These precision measurements of flavor observables are very important. We have some anomalies still. Maybe some of those anomalies are real. I didn't talk about all of them. Maybe some of them are real. Or maybe there are other anomalies that will be discovered in the future. precision measurements of standard model observables remains an extremely important way to indirectly find new physics. Okay, you're not producing a new particle, right, directly, but you're seeing its virtual effects. So I think I remain hopeful that those precision measurements will come up trumps at some point for BSM physics. Of course, they do a great job in testing the standard model, but maybe at some point an anomaly will be confirmed. Higgs factory of one sort or another, FCCEE, the Circular Electron Positron Collider project in China, the International Linear Collider project, which if it happens will probably happen in Japan, but maybe it's these things, which are designed to be Higgs factories, are very important. Just like after the discovery of the Z boson in the early 1980s, LEP was built at CERN in order to study the hell out of the Z boson, right? And to this day, it provides very important constraints in all of these theories of ours. So we've now discovered the Higgs particle. It's just scientifically justified to study the hell out of the Higgs and try to see if the Higgs particle really is precisely the standard model Higgs or something a little bit different. For example, it's still possible that 10% of the time the Higgs decays into dark matter, right? It's still possible, right? So that sort of a discovery would be rather dramatic. So you know, it's another kind of precision test. We have flavor observables. We also have precision Higgs physics that I hope will be done at some machine, you know, over the next, before I'm 90, okay? On the cosmological side, we have inflation. A generic prediction of inflation is that there should be tensor modes. So basically primordial gravitational waves. So, you know, if that is discovered in CMB, you know, that would be very important. Future gravitational wave observatories, the ones out in space, like ELISA and so on, those can probe conditions in the early universe, things like the electroweak phase transition or maybe phase transitions in the dark sector that cannot be accessed, you know, terrestrially. So, you know, there are a lot of papers being written about the gravitational wave signatures of various beyond standard model things. So, you know, there is reason to be hopeful. On a very short time scale, the most likely things to me are some dramatic dark matter discovery or some flavor physics discovery. By short time scale, I mean several years, all right? Longer term, some discrepancy in between the Higgs that exists in real life and the standard model Higgs that exists on paper.
I was somewhat surprised that you didn't mention neutrinoless
Double
double
beta.
beta decay as one that could, you know, potentially really reveal something about the mass structure of the universe.
Thank you. I always forget something. So if neutrinos are their own antiparticles, which is entirely possible and in fact can be argued to be theoretically favored, then lepton number conservation is violated by 2 units. And so this process called neutrinoless double beta decay should happen. So double beta decay is where basically 2 beta decays happen. But in the neutrinoless case, what you see are 2 electrons or 2 positrons coming out. You don't see any, there are no neutrinos. And so lepton number is violated by 2 units, either plus or minus. So yeah, there could be a breakthrough on that front. I should have mentioned that. I didn't have my list prepared. And I think very important, you know, if I'm asked what do I most want to know about neutrinos that we don't know now, it's whether they're Dirac or Majorana.
I just wanted to ask you about your opinion, and since you said you're working on axions,
Yeah.
not on axion phenomenology, if there's any way in axion setups that you're aware of where one could understand why there's not that much more dark matter than matter in the universe,
Oh.
sort of the same order of magnitude.
Yeah, yeah. Well, because
Possible?
I wish. I mean, actually, my favorite dark matter candidate is something called asymmetric dark matter for precisely that reason. So I kind of obsess over that question of, so the CMB measurements have established that the dark matter mass density today is about 5 times that of the ordinary matter density. And a factor of 5 is order 1 in cosmology. So it looks like these 2 different kinds of matter might be related in some way. It's at least a reasonable hypothesis. Or there should be some rationale for that, because in most theories of dark matter, that is a coincidence, right? Axion dark matter, that is a coincidence. WIMP dark matter, that is a coincidence. Because the physics has got nothing to do with where the baryon asymmetry comes in, which is what sets the Rayleigh density of ordinary matter. So indeed, I think that may be a clue to the underlying nature, particle nature of dark matter, or it is a coincidence. So, yeah.
So Ray, your talk deeply offended me because I spent most of my life working on supersymmetry and planification.
Yes.
And about a week before the WBM paper, I wrote a very long review on G-2, saying how important that problem is. But okay, seriously, if you were one of my PhD students, what would you recommend for the student to
work on?
Yeah, to work on.
I mean, I do have to answer that question from time to time. Well, definitely, look, all three of those empirical things are very important. So, different ideas for neutrino mass generation, different ideas for what the dark matter is. Like, there's a lot of focus at the moment in the community about just exploring dark matter parameter space. So say with WIMPs, you have really two things. You can have more complicated theories, but the two things are typically plotted. The mass of the WIMP and the cross-section of the WIMP, the way it interacts with standard model nuclei. And you have these exclusion curves from present experiments. And the sensitivity of present experiments dies for WIMP masses below a few GeV. So there's a lot of focus, and people in my department work on this, different ways of searching for dark matter that has a mass lower than these traditional direct detection experiments can access. So, a lot of that sort of thing is being done. There's a lot of theorists inventing different ways of doing experiments, searching for different kinds of dark matter. That's become a game, So baryogenesis, inflation. So I mentioned Starobinsky and Higgs inflation. Well, I learned only a few weeks ago that there's a new measurement by ACMB collaboration, ACT, that challenges these because it gets a parameter that's a bit bigger than it was thought to be. So I think, and then Linde has been writing, about that in the last month or so. So I think that is, implications of inflation are important. But I think there's a whole raft of things. And what's happened now is that there's more of a plurality of efforts on different things. So some people are trying to find WIMPs, other people are trying to find axions, other people are trying to observationally get evidence for primordial black holes. So it's not just all about WIMPs anymore. Axions were the forgotten dark matter candidate for a while, but now they've made a resurgence. Right? Yeah.
Now, it's a question about dark energy.
Yeah.
So you mentioned the DESI results. But you didn't really mention dark energy in the context of beyond the standard model.
No.
Do you think it's a separate? Where do you see dark energy fitting into this?
First of all, I'm not an
expert.
Yeah, sure. I'm not an expert on dark energy, so I'm not the right person to ask. I mean, until the DESI results, it looked to me all the world like it was a cosmological constant. And that to me was not, it wasn't surprising that the cosmological constant existed. Of course, one can argue that its value is much smaller than we expect. And it's not just compared to Planck mass to the fourth, it's also compared to electroweak scale to the fourth or QCD scale to the fourth. Even with those, there's many orders of magnitude different. Like, for example, we have the Higgs potential in the standard model, and there's no reason for the minimum of it to be exactly at 0, right? And if it's different from zero, that contributes to the cosmological constant. You know, I think if it is dynamical dark energy, then that brings in a whole new ball game of cosmological model building, crossover with the particle physics. I haven't worked on that. I don't have anything profound to say about it, except it's very important if it gets confirmed. But you know, I think an extraordinary result like that requires, you know, real confirmation. You know. Yeah.
Might have time for one more question. There's one.
Just a follow-up on that, even if dark energy is just a constant, cosmological constant, there is still this problem that it being vacuum energy or coming from vacuum energy, right?
Yeah.
Is that something that we can solve through beyond standard model physics, or is that something?
Yeah, well, that's, you know, that's the big question. If it is a cosmological constant, you know, I've measured. I mentioned the value of the Higgs potential at its minimum. That's from a particle physics point of view an unobservable parameter, but it's a contributor to the cosmological constant. QCD contributes to the cosmological constant, and so and both of those numbers are much higher than the observed value. Setting aside DESI for the moment. So you know, how do they conspire to almost cancel? You know, with a primordial cosmological constant. That is the $6 million question, and no one's been able to answer that as far as I'm aware. And I certainly don't have any ideas about it. But it's certainly curious. It is a genuine problem. I mean, I heard one prominent early universe cosmologist argue that, well, it could be that we simply don't understand how gravity couples to vacuum energy, that there's something peculiar there. You know, could be.
Okay, I suggest we continue the discussion in the kitchen. For those of you interested in further discussion and or tea, coffee, and cookies. And that we thank Ray again for this nice talk. Thank you.